images, we also need to extract features from audio signals to more efficiently describe audio features. So recall that why do we need image features? Because if we faithfully store the pixel value of each pixel, then we need a lot of storage, and we cannot capture the characteristic of images. So this is the same case in audio signal. We also need to extract some features, maybe based on statistics, maybe based on the shape of the signal. We have to more efficiently describe audio signal. That is called audio features. And based on the unit, we extract the audio features. The audio features can be roughly categorized into frame level features and clip level features. The frame level in audio signal, we usually divided the original audio signal into audio frames. And as we said before, we assume that in each audio frame, the property of the audio signal in such short time period is stationary. And then we can transform this short time audio signal into frequency domain. Therefore, the audio frame is defined as a group of neighboring samples which lasts about 10 to 40 milliseconds. And this is a very, very short period. For audio clips with sampling rate 16K, how many samples are in the 20 millisecond audio frame? So you can imagine that we sample 16K sample points per second, and 20 millisecond means 20 divided by 1000. Therefore, there are 320 sample points in this 20 millisecond audio frame. Okay, and within an audio frame, we can assume that the audio signal is stationary, so that we can apply the Fourier transform to transform the original audio signal into frequency domain. And this is called audio frame. We can extract feature from such short time period. But for more appropriately describe some audio characteristic, 20 millisecond or maybe 40 millisecond may be too short to reflect the characteristic. For example, if we want to classify the given audio signal into one type of music, like jazz or classical or rock and roll, okay, we cannot determine the music genre, music class based on such short time period. Therefore, we need to aggregate, we need to accumulate the characteristic of many audio frames. That is called an audio clip. A clip consists of a sequence of frames, and a clip level features usually characterize how frame level feature change over time. Okay, and in the following material, most of the content are coming from this paper. This paper was published in year 2000 in IEEE Signal Processing magazine, and I highly recommend you to read this paper because it's quite simple, but it is very important for you to understand the audio features. Here is an illustration showing the relationship between frame and a clip. So, given this audio signal, we can divide it into overlap of audio frame. So this one audio frame may last for 20 milliseconds or 40 milliseconds, and we aggregate uh, a numbers of audio frames to be a clip. So fixed length clip that may last for 1 to 2 seconds, or very length clips. And then how can we extract clip base feature? That is basically we find the distribution of the frame base features or some statistic of the frame base features to form the clip base features. So both frame and clip may overlap with their previous one. So in this example, the two consecutive clip do not overlap, but sometimes we can also design the overlap version like this. Now we start from frame level features. Most of the frame level features are inherited from speech signal processing. As we know, the history of audio processing is longer than that than the visual processing. Starting from World War II, the period of World War II, there have been many studies on audio signal processing because of the requirement of transmitting sound, okay, or transmitting signal. So signal processing or audio signal processing, speech signal processing have longer history than visual processing. So when we start to do audio analysis, the frame level features are mainly based on the study of speech signal processing. And we can roughly divide the features into two types: time domain features and the frequency domain features. As we mentioned above, our human ear is working based on frequency analysis. Therefore, in early years, many audio features were proposed in the time domain. However, recent work found that the frequency domain features work even better than the time domain features. And in the following, we will use capital N to denote the frame length and the SNI to denote the ith sample in the nth audio frame. Because right, as we mentioned above, each audio frame consists of many sample points, just like the example we showed you before. The 20 millisecond audio frame consists of 320 sample points. The first simple feature is called volume, or sometimes called loudness or energy. This feature is quite simple. Volume is a reliable indicator for silence detection. So how loud of the given audio sound is measured, and it's especially useful to detect silence segment, which may help to segment an audio sequence and to determine clip boundary, because between different clip or between different sentence, there may be several silence segments. So how can we calculate? How do we quantize volume? It's approximated by the root mean square of the signal magnitude within each frame. So we can see the formulation here. We just sum the sample point, the sample value, the square sample value. Okay, we sum all of them, and then take the average and the take square. So that for the nth audio frame, it's quite simple to calculate the volume feature for the nth audio frame. We just sum the square sample values and then take average and then take square root. And remember that the volume of an audio signal depends on the given value of the recording and the digitizing device. So based on different device, although maybe a human spoke for the same volume, but according to different capture device, according to different microphone, the volume stored in the computer system may be different. So remember to normalize the volume for a frame by the maximum volume of some previous frame. So in this example, for example, this is an audio, and then we may segment it into many audio frames, and we can calculate the volume value V1, V2, V3, and so on for each frame. And remember, for example, V1, remember to divide it by the maximum value of V1 to Vn. This is called the normalization process. Okay, and this is necessary because the volume of an audio signal depends on different capture device. So remember to do normalization, then you can compare different audio signals. The second simple feature is called zero crossing rate. Okay, and remember that for a given audio signal, it may look like this. Okay, and the so-called zero crossing rate is in a second. How many zero crossing like this? From positive to negative, so there is a zero crossing here. From negative to positive, there is another zero crossing here. So we just calculate in average for every second, okay, how many zero crossing in this audio signal. Okay, so we count the numbers of times that the audio waveform cross the zero axis, and the formulation is like this. So we take the sine of the I sample and the size of the I minus 1 sample, and check whether their signs are the same. If they are different, that means there is a zero crossing. Okay, and we sum all zero crossing case. Okay, and then because if there is a positive to negative, there is highly probably there is a negative to positive. So we divide it by 2, but this is not very important. And the term fs divided by n here is to transform this value to a second base feature. So the ZCR is the numbers of zero crossing per second, where fs is the sampling rate and n is the numbers of samples in each audio frame. And the zero crossing is one of the most indicative and robust measure to discern on voice speech. You can see that when there are many zero crossing, it's probably that this part of audio signal has higher frequency. Okay. And in on voice speech like this on voice speech, the waveform look like this. There are many zero crossing. But for the vowel like or these are vowels, and there are less zero crossing. Okay, so typically voice speech has a low volume but a high zero crossing rate. So by combining the volume and the zero crossing, we can discriminate the given audio segment is a silence or just an on voice speech. Okay, so using zero crossing and the volume together, one can prevent low energy on voice speech frame from being classified as silence. Pitch is another important audio features. Pitch is the perception how we perceive the frequency of the given audio sound. Like if we say that some audio sound has higher pitch, that means ha. Another audio sound with low pitch is ha. Okay, so you can imagine what is pitch. And pitch theoretically and mathematically, pitch is the fundamental frequency of an audio waveform. So if the fundamental frequency is high, then we say that it's a higher pitch, and we may perceive a higher sound. And then we normally only voice speech and harmonic music have well-defined pitch. Okay, like the R, E, U, A, O. This is voice speech, and music and most of the music part are harmonic. And this terminology, if you are interested in the definition of this terminology, please take digital signal processing. Okay, and based on the time domain signal, we can do the pitch estimation based on the following two methods. We rely on the computation of the short time autocorrelation function, RNL or AMDFANL. Okay, the RNL is defined like this. We calculate the multiplication of SNI and the SNI plus L. So this is what, given an audio frame, there are many uh, uh, sample point, and then if we define the value L as V, that means we will calculate the multiplication between the first one and the third one. We will multiply them. Okay, and if the sample point, the sample value repeat for every three sample point, then the multiplication between 1 and 4 may be larger. Okay, and this is called autocorrelation. That is, we try to calculate the correlation between the sample point in the same set. Okay, and this is called the autocorrelation when they are apart from L is equal to 3. And of course, we can define L is equal to 0, 1, 2, 3, and so on. Okay, and this is the first way. The second way is called the average magnitude difference function, AMDF. So we simply divided the SNI by SNI plus L. That means if for example, in this case, if SN1 is very similar to SN4 periodically, then the numbers of this value will be quite small. So this is the so-called AMDF. And if we try different L, and we calculate the RL and the AL, we may see the effect like this. Usually, for voice, speech, or harmonic music, we may find some value in RL or AL. Okay, value exists in voice and a music frame, and vanish in noise and on-voice frame. So for a voice and a harmonic music frame, there may be some value, and you can see the value may be periodic. So according to the periodicity of the value in RL or AL, we can estimate the pitch based on the time domain signal. We can estimate the pitch. However, all the features we mentioned above, including volume, zero crossing rate, and the pitch, that cannot be that cannot very well capture the signal characteristic. So another way to view the signal is to transform the signal into the frequency domain, and then based on the frequency domain, we can design many spectral features. Okay, so when we transform each audio frame into frequency domain, we can accumulate all the and take them together to make this visualization, and this is called spectrum. Spectrum means the Fourier transform of the sample in this frame, and here we can see that at any time instance, there is a audio frame corresponding to this time instance, and when we transform this audio frame into frequency domain, we can see the energy distribution of this frame. And if we put all audio frame together and put all frequency distribution together, we may form a visualization like this. Okay, and this is called spectrum. And in this example, we have three different audio signals, including commercial, news, and sports. And from the time wave, from the waveform, we can perceive that okay, the news signal is different from the commercial and sports. But you may just subtly feel the difference between commercial and sports, but you cannot accurately quantify the difference between these two audio sounds. But if we transform these audio signals into frequency domain and show you the spectrum, you will see that okay, the news audio signal is the spectrum of the news audio signal is really different from commercial and sports. And then you can also see that the spectrum of the commercial sound is quite different from that in sports sound. Okay, and this effect cannot be easily seen if we uh, just observe the time domain signal. So this is the value of the spectral feature. The difference among these three clips is more noticeable in the frequency domain than that in the waveform domain. So this is the main idea why we need to design spectral feature. Let Sn omega denote the power spectrum of the front end. So here you can see the omega denote the frequency, and the n denote the index of the audio frame. And the power spectrum means the magnitude square of the spectrum. That means at the frequency omega, the sound energy, that is called Sn omega. If we think of omega as a random variable and the Sn omega normalized by the total power as the probability density function of omega, then we can define the mean and the standard deviation of omega like this. The first spectral feature is called frequency centroid, or sometimes we call it brightness. That is the integral from 0 to infinity, and omega times Sn omega d omega. This is actually the average or the augmented average of the energy in the frequency domain, and then divided by the total power. Therefore, we can see what is Fc, and that means at the audio frame and the average frequency. Okay, the average frequency or the frequency centroid. Like if there is um, a frequency like something like maybe this, and then the frequency centroid may be around here. Okay, so this is the FCN. Okay, and if we calculate the variance of the energy distribution, then that would be omega minus FCN. So this is the omega minus the average and the tech square and multiplied by Sn omega and divided by the total power. Then this would be the physical meaning of this value would be the variance of the energy distribution in the frequency domain. And this feature is called bandwidth. Okay, the bandwidth here is different from the terminology bandwidth in the computer network. Okay. The third spectral feature is called subband energy ratio. Okay, we try to calculate the ratio of the energy in the frequency subband to the total energy. So we can divide it. For example, this is the frequency domain, and then we may divide it, this frequency domain into several frequency range. Okay, and for example, BEI means we integral from omega L to omega U, and then take the spectrum square. We integrate them. That means we calculate the energy, we accumulate the energy between omega L to omega U. So we basically calculate this energy distribution. This is called BEI if we consider the I's frequency band. And BERI is the band energy ratio. Okay, so we divided the BEI value we divide the BEI value by the total band energy. So we got the ratio. So when the sampling rate is 20K, the frequency range for the full subband that can be divided by 0 to 630 hertz, 630 to 1720 hertz, and so on. And we can calculate the ratio in this frequency band to others, and the ratio of this frequency band to others, and so on. Okay, and you can see here, for the lower frequency band, we divide it in a finer way. Okay, for high frequency range, we divide it just very roughly. So this corresponding to what I said before. We human ear are more sensitive to lower frequency signal. Okay, for high frequency signal, we are insensitive. Okay, and this feature was proposed in this very famous article published in 1998, Journal of VLSI Signal Processing. Okay, and the author here is quite famous, Su-Han Chen. Okay, he is also original from Taiwan, and he first teach at Carnegie Mellon University, and then moved to Cornell University, and in recent year he moved to Nanyang Technological University. The next audio feature is called Spectral Flux. Okay, Spectral Flux is defined as the average variation value of spectrum between the adjacent two frames. So here we can see this is the log magnitude. Okay, at the nth audio frame. This is the log magnitude of the n-1 audio frame, and then we just take the difference between them, and then square, and then sum, and take average. This is called spectral flux. Okay, and we have different notation here. A and K is the discrete Fourier transform for the nth frame of the input signal, and this feature was proposed in this paper published in IEEE Translations on Speech and Audio Processing, year 2002. Also, this is a very, very famous author here, Hongjiang Zhang. So you still remember when we talk about video shot change detection, there is a paper published in 1993 in ACM Multimedia System Journal. The author is also Hongjiang Zhang. Okay. So the spectral flux value of speech are higher than those of music. So the physical meaning of the spectral flux is the difference, the energy difference between consecutive audio frame. And for music, because the sound play continuously. Okay, and for our human speech, because we have very short silence between different words. So the SF value for speech are often higher than those of music. Okay, and the environmental sound is among the highest, and it change more dramatic than the other types of signal. And this is an example showing the first part is speech. Okay, the second part is music. The third part is environmental sound. And we can see the difference between them. The music has very low SF value, and the speech part has larger SF value, and the environmental sound has the highest SF values. The next one is called Spectral Rolloff. Okay, these features were proposed in 1997 proceedings of ICASP, IEEE Conference on Audio, Acoustic Speech and Signal Processing. Okay, the definition of spectral roll-off is the 95 percentile of power spectrum distribution, and this measure distinguish voice from unvoiced speech. The value is higher for right skew distribution. Okay, so what is 90th percentile? So we just compare two distribution. The first distribution is like this. The second distribution like this. The so-called spectral roll-off is we accumulate the energy until we accumulate until the 95% of the total power. So in this case, we may accumulate the energy until here, and this value is called the spectral roll-off. And for this distribution, the 95% percentile may be like this, maybe here. So this is the spectral roll-off R1, and this is R2. And if the distribution is left skew, then R1 will be less than R2 if R2 is the right skew distribution. Okay, and what is right skew? That means more energy concentrated on the high frequency part. What is left skew? That means more energy are concentrated at the low frequency part. So it's a very simple description about whether the given audio signal concentrate more on lower frequency or high frequency. And unvoiced speech has a high proportion of energy contents in the high frequency range of the spectrum. So unvoiced speech is more like this distribution. This is a measure of the skewness of the spectral shape. The next audio feature is a very, very important one. That is called MFCC, male frequency spectral coefficient. This is one of the most popular features in speech audio and music processing, and it has been demonstrated having the most promising performance in audio classification, audio analysis, and many others. The idea of the MFCC is that we also talk about our human ear is workable based on frequency analysis. So some oral cells are more sensitive to some frequency band, and another set of oral cells are sensitive to another frequency band. And the MFCC try to capture such characteristic. And first, the step is as follows. We first segment incoming waveform into frame, and then we compute the frequency response for each frame using DFT. Okay, so these two steps are the same as previous. We transform the audio signal, the audio frame, into the frequency domain. And then we group magnitude of frequency response into 25 to 40 channel using triangular weighting function. That means we divided the frequency domain into 25 to 40 frequency bands, and according to a predefined triangular weighting function. Okay, and the different frequency band may have some overlaps, and we also give some weight on the energy in each frequency band. We then compute the log of weight magnitude for each channel. And then we take inverse DCT or DFT of the weighting magnitude for each channel, producing around 14 spectral coefficient for each frame. So let's go into the details. One of the most important idea of MFCC is the definition of male weighting function. Human pitch perception is most accurate between 100 Hz to 1000 Hz. So we would like to divide this frequency range linearly, and we divided the frequency range above 1000 Hz arithmetic. Okay, and a male is a unit of pitch defined so that pairs of sounds which are perceptually equidistant in pitch are separated by an equal numbers of male. This is an illustration showing how we divided the frequency domain into frequency bands. Below 1000 Hz, we just linearly, we just equally divided it into a frequency band, but with overlaps. And above 1000 hertz, we divide it more and more roughly, okay, until when a very high frequency like 6000 hertz to 8000 hertz, we just put them together into only one frequency band. Given the special design of dividing the frequency domain into frequency bands, we will extract energies in each frequency band and then take Fourier and then take a transform again to get the spectrogram. And from spectrogram, we will extract spectrogram coefficient. And we will describe more details when we introduce you some advanced application about the MFCC. So all the all the features we mentioned above are feature-based features. Okay, the feature-based features may be the frame-based features, and the frame-based features can be extracted from the time domain or maybe from the frequency domain. Now we describe the clip level feature. To extract the semantic content, we need to observe the temporal variation of frame features on a longer time scale. So basically, the clip level feature and the frame level features are different at a unit. And because we want to capture the temporal variation of frame features. So basically, the clip level features are statistics of frame features. Like we may devise some volume-based feature, like VSTD, that is the volume standard deviation. So we may consider many frames, and then we calculate the standard deviation of the frame-based features. Okay, the frame-based volume feature. Okay, this is called VSTD, or maybe VDR, the volume dynamic range. Okay, so in this clip, what is the highest volume? What is the lowest volume? And then the difference between them is the volume dynamic range. Or maybe the percentage of lower energy frame, like the proportion of frame with a rooming square volume less than 50% of the mean volume. Okay, what is the percentage? Or the non-silence ratio. Okay, the ratio of the numbers of non-silence frame in this clip. So all these are calculated based on frame-based volume features. And also maybe based on ZCR, we can also calculate some clip-based ZCR feature with a speech signal, low and high ZCR period interlengths. Okay, and then we can calculate ZSTD, standard deviation of ZCR, standard deviation of the first order difference, third central moment about the mean. Okay, so these tools are based on statistics. The total numbers of zero crossing existing of threshold, that's more like we try to removing the effect of silence. Okay, and the difference between the numbers of zero crossing above and below the mean values. Okay, here is an example showing the zero crossing rate contour for music and for speech, and you can see that for speech, it tend to have higher zero crossing rate over time. Also, the pitch-based clip level feature can also be divided, like the standard deviation of pitch, the smooth pitch ratio, that is the percentage of frame in a clip that have similar pitch as the previous frame. Okay, so we measure the percentage of voice or music frame within a clip. Okay, because for voice and music frame, we may have higher smooth pitch ratio. And then the non-pitch ratio, like that is the percentage of frame without pitch. So this is to measure how many frames are on voice, speech, or noise within a clip. And this is an example showing for the commercial, news, and sports audio song. the evolution of the pitch feature.